Thank you for the opportunities to present. My name is Professor Cheng from Newcastle University in Singapore. Today, the title that I'm going to present is Electro-thermal Model of Lithium Battery under the Parametrics and Temperature Variations. The content I'm going to present is as usual. We will start with some background. We will discuss the electrical battery cell model that you should know well. Then we will discuss about combined electro-thermal model with lithium-ion phosphate battery cell, and followed by electrothermal battery cell step model, and the parametrizations of electrothermal cell models, experiment result, conclusion, and then the future works. So as a background, the lithium-ion phosphate batteries has become popular for renewable energies, storage device, electric vehicles, and smart grids. Internal and core temperature of the battery cell can differ from the surface temperature under certain operating conditions. So you can see that for these battery cells, there's cell temperatures, and there's also the ambient temperatures or this ambient environmental temperatures. So that will affect the batteries. Okay, so this is something that I will try to model the thermal into the electrical models. So a set of model parameters obtained at a certain temperature is not robust for real-time operation. So in most of the models, they often get the model parameters at a certain temperatures, which is not so robust because in the real-time operations, the batteries actually operate in a different ambient environments. So therefore, we using a thermal model to predict the core temperatures under different operating conditions can enhance the overall model in the battery management systems, which we know is called BMS. So in this presentation, the electrochemical thermal model will not be discussed. So we will not discuss on the chemical portion, but we will discuss on the electrical and the thermal models. So instead, the thermal model followed by electrothermal model will be discussed, and the heat generated during the rapid charge and discharge cycle of the Sony US 18650 lithium-ion battery cell at different current was also studied. So the thermal behavior such as the core and the surface temperature of the cell show a differ of around 0.2 degrees to 3 degrees using 1D thermal conductive and convective heat transfer. So this is one of the literature findings that we have discovered, that the difference is about not more than 3 degrees Celsius with this 1D thermal and convective heat transfer. However, the electrothermal behavior and the influence of ambient temperatures and also the uncertainty of these thermal parameters of the battery stacks, okay, it's not just one cell, but in terms of many cells are not studied. So the electrical model under varying ambient temperatures and thermal model parameterizations under the uncertainties for battery cell and stack using the lithium-ion phosphate model is the 26650 are marginally discussed. So that forms the part that we are going to discuss today. And we will know that the electrothermal model is likely to have a higher precision in practice due to the simplicity in the parameter identification as compared to the chemical model. So as a result, the 1RC, a thermal-based model of this lithium phosphate cylindrical cell model 26650 with consideration of the surface, core, and ambient temperature variation are required. So hence that will establish what we are going to study today. So the battery specifications is a very common one, is the A123 systems, ANR 26650 M1B. And the following specifications that you can see, look at the chart on the right hand side, which is commonly available in the literatures or even in the internet resources. So the electrical battery cell model, you can see there is the 1RC models. So the single RC models you can see on the left hand side, and the right hand side is the thermal model of the lithium-ion phosphate cell. So you will see that the voltage across the RC branch is U dot is equal to -1 of RC1 U1 plus I over C1. And the terminal voltage, which is the UT, is basically the UOC, and UOC is defined as the difference between the two voltage terminal when disconnected from the circuit, minus the U1 minus R0 I. Alright, so this is a very common electrical these equations. Alright, and then you can see on the right hand side, we will further develop how to model the thermal into the electrical model. Alright, so for the open circuit voltage, the OCV, or in short UOC, can be defined as follows: the K0 plus K1 SOC plus K 2 natural log SOC plus K3 natural log bracket 1 minus SOC. And the SOC here is the state of charge. Okay, can be estimated by here we just use the ampere hours AH counting methods. Okay, using the current and the nominal battery capacity in AH, which here we call is as Cn, and this is how we determine what is the SOC. SOC dot is equal to minus I over Cn. Okay, Cn is the nominal battery capacity. So if we try to differentiate this UOC, in short is UOC dot, you will give us the K1 SOC dot plus K2 SOC dot divided by SOC plus K3 SOC dot divided by SOC minus 1. So if you go through a simplifications, alright, or we further simplify this, not going through in the detail, but you will see that the U dot T you will get in terms of minus 1 over R C1 UT. Remember UT is the terminal voltage, minus bracket these whole terms times I plus K0 over R1 C1 plus K1 over R1 C1 SOC plus a functions that is consist or in terms of SOC and I. So in this case, this function will look like this. So I try to extract this function out so that we can actually try to form a state space equations. So what about the thermal battery cell models? The temperature distributions in the longitudinal direction is more uniform. So this longitudinal direction is more uniform than the radial directions due to the higher thermal conductivities. So the dual states approximations of the thermal models in radial directions is commonly defined as this, something that you can find from the literature. You'll find that the change in the surface temperatures over the time is equal to the TA is the ambient temperature minus the TS surface over RSCS minus TS minus TC over RCCS. And then for the core temperatures, which is the core, okay, this C and S refer to core and surface respectively. Okay, you can write this as TS minus TC over RCCC plus Q over CC. So this Q is the heat generations. In this case, we use these formulas, which is equal to I squared RD, just a lump resistance. So just to make sure that you know the symbols, the CC, CS is the heat capacity of the core and surface respectively. TA is the ambient temperature, TS is surface temperature, RS and RC is the convection resistance on the surface of the cell and the heat conduction resistance in the core of the cell respectively. Okay, so C means core, S means surface. We combine the electro and thermal together and we form this cell model. So this is the states and output equations of any I battery cell, which you may have 1, 2, 3 or so on. So these are state space equations. If you try to formulate that, as you know, when you write a state space, you need to know what is the states first. Okay, and then you try to factor the states out so that you can find out what is the A, but you must know what is the U. Okay, U in this case is the current. Alright, and then you can find out the B, and those terms, the non-linear terms, I just put this outside the state space equation. So this can be called a non-linear state space equations. And this is the output equation, usually defined by what is the output that you want to see. Okay, so the electro-thermal battery step models, so you can see that the heat generations Q is equal to I squared RD, as I mentioned in the previous slide, is similar for each cell. So we assume that the cell is similar and they are connected in series, and the surface temperature of the cell number 1 is quite close to cell number 2, because in this arrangement you can see that they are quite close together. I mean, they are not touching one another, but they are close. Alright, so however, the surface temperature of the cell in the stack can be different as the heat is transferred from one cell to another. So you can see that the heat can be different because the convection is moving from the left to the right. So you can see that the heat actually travel, okay, from the left to the right as well. So this is something that will be taken into account. Energy balance of the battery cell due to conductions and convections under constant heat generation Q can be written as such. Okay, if you go through your heat transfer, you will find that you can write this conduction and convection as such. Okay, and where this delta K, which I try to simplify as 2 pi L over 1 over RH plus natural log R2 over R1 bracket RKC. So Kc is a constant, and there are some constant. H is the convection coefficients. So these are some constant that we need to find out. In fact, this also what I condense this as delta K. So take note that Ts is the surface and Ta is the ambient temperatures. So the surface temperature of the eye cell can be sequentially computed as follows. It can be seen that the surface of temperature is a summation of the ambient temperatures and a multiple of the Q over delta K of each cell that is arranged in series. So you can see that surface temperature is Q over delta K plus Ta. So you go for the next one, the surface temperature of the next cell, which is cell number 2, is Q over delta K plus Ts1, where Ts1 is basically, you can move this first equation into the next equations, and so on and so forth. So you can stack all this into one whole equation, which we call this as Tsi, which is equal to Q over delta K. I, that I depends on the which number of cells you are talking about, plus in total the Ta, which is the ambient. This ambient will surround the battery cell, but you may argue that this Ta at this point may not be same at this point, that point, and so on. So we can say that it's almost similar. So that's the assumption that we have to make. So the combined electro-thermal model of the lithium-ion phosphate battery cell, you can see that the thermal model will compute the surface and the core temperatures. Alright, so if you look at this model part, we compute the core and the surface temperatures, and then we will use the ambient temperatures as input to the thermal model. As you can see that we use the Ta as the input to the thermal model, and the surface temperature we use to determine the temperature dependent parameters of the electrical model. So this Ts will go into this electrical model, as it's difficult to measure the core temperatures. So the core temperature is quite difficult to measure if you try to unroll the gel. So you will find that you need to put some sensor into it, and then you have to roll it back. So there will be some skill involved. At the same time, it also will affect the properties of the battery cell. So we just assume that the core is quite similar to the surface. So the core temperature will be estimated by the least square approach. So I mean, it's difficult to measure, but we still have to try to estimate it by the least square approach. Right? So this is something that we will do, and the electro-thermal model can estimate the terminal voltage, therefore by the core and the surface temperature of the battery cell. So this is something that we are doing here. So the parametricizations of the electro-thermal cell model. So we identify the open circuit voltage, the internal resistance, capacitance, and the resistance of 1 RC pairs. So you can see here, you try to say that the 1 RC is quite a close fit to 2 RC, and even you can try the 3 RC. So we try to make it simple, so we choose a 1 RC as the electric cell models. So the parameterizations of the electro-thermal cell model, you can see that we try to obtain the electrical parameters. The battery cell is first fully charged, so you need to fully charge it to reach a full SOC to 1 under the typical constant current, constant voltage, in short CC and CV conditions, before the terminal voltage is relaxed for at least 45 minutes to reach the equivalent. So we need to let it stabilize first, and this is how we determine what is the AH. So it's the currents of discharging, just integrate it or basically sum it and just divide by 3600. Okay, so we want to make it into the hour, so we divide by 3600. So the cell is then discharged to SOC value of 0.9, okay, with a current of 0.8 C or 2 amps. Alright, so that is the targets that we are trying to do, where 1 C is measure of the charge and the discharge current with respect to the nominal capacities that we know here. So the current is terminated to relax the battery for 45 minutes to reach the equivalent. So from here, the jumps in the voltage, the change in the U0, which can be equal to the R0 times the current, the Ohm's law. Alright, so we can determine the U0, we can know the I, we know the R0. Okay, so but these multiple R0 values determines from the pulse test. Okay, so a mean values that represent R0 at different ambient temperature SOC values will be determined. Okay, we don't just get the one R0, but we try to get the mean values. So in addition, the value of different SOC range can be expressed as follows. So we know the R naught, a function SOC. So this is the expressions that we have established where A, B are constants. Then the voltage transient during the relaxation is used to estimate the R1 and C1 parameters. So you can refer to this. So once it try to relax, but basically we try to relax it, which is another curve that you see here. Okay, so we use to estimate the R1 and C1. So these are the formulas that we are using. So we know the U1, so we know the I. So we will have to find out, okay, what is the R1 and C1. So just note that the TRC is the pulse period prior to the relaxations. So the R1 and C1 is used to minimize the voltage least square errors using the cost functions. So this is the U1 minus the U1 data that we calculated. We square and sum it and we try to minimize it, okay, so that we can find out what is the R1 and C1. So the steps to determine the R0, as you can see, and R1 and C1 in the previous slide can be repeated, okay, until the terminal voltage reach the final cutoff voltage of 2.5 or sometimes 2.6 volts, okay, which is stated in the specifications of the cell. So during the test, the battery cell is inside these ovens where the ambient temperature was controlled at a few set points. So we control at several set points at 5 degrees, 15, 35, and 45. So you may ask, why don't you reach 50 and so on? But we try to remain as simple as possible, but it can be always refined. So the difference between the discharging and the charging voltage due to hysteresis can really exist, because when you try to charge and discharge, they don't follow the same path. So to circumvent this, the average value of the discharging and charging voltage is used as the OCV. So the value of OCV, that is the terminal voltage at equivalent, occur at about 45 minutes relaxations, was identified from the results of the pulse discharge test under 25 degrees Celsius. Okay, so we can do it for some other temperatures. So the OCV for each SOC value estimated by AH counting methods can also be plotted. So with that, we can plot the OCV over the SOC. So the cell model parameterization in thermal is something that we will do next. As the measurement of the core temperature is difficult, the approach uses only the surface temperatures. So remember we try to estimate the core temperatures. So here we measured the surface temperature at low current, and the ambient temperature can easily be measured as what I mentioned. So the parametric models of the thermal model in the S domain is written as such. Alright, so remember these are very common regressions formulas. So we know that the theta is the parameters, W is the observations, and this is the regressor, including the measured parameters. So these parameters you can see from the right hand side, the regressor, parameters, observations, and these are the physical parameters. Just take note, when we do these formulations, so we need to use the time domain equations, okay, for the thermal model, and then we need to do a Laplace transform into here so that we can parameterize into this form, so that we can try to estimate the parameters. So the least square approach is applied to estimate the theta. So the whole idea is that we want to determine the theta. So hat means the estimations. Okay, so the parameters estimates of RS, RC, and CC can be determined using the following relationships. Okay, so take note that once you find the theta, and you know the theta is delta, sigma, and mu, so from here you will find out that the following parameters, okay, which reside within the theta parameters. But not only this analytical approach, we also need to try to validate our theory with the experimental results and the validations for battery cell and also the step models. So the experiment tests are conducted, as I mentioned, using the lithium-ion phosphate battery cell of type AMR 26650 M1B to validate the proposed electro-thermal models. So the CCCV test is actually performed, okay, in these ovens, okay, at several temperatures, which is the ambient temperatures, and this is the setup that we have shown here on the right hand side of this figure, and take note we have 5 degrees, 15, 25, 35 and 45 degrees. So inside the chromatic chambers, okay, to obtain the temperature dependent parameters. So the current is generated by the direct currents, okay, the electrical loads, while the battery cell are charged at the programmable DC power supply to control the voltage, and the host computer link between the data acquisition device and the battery cell. So the DAQ device will control inputs and output data at the acquisition rate as 1 Hz. So as you know, the current sensor measures the currents, and we have the thermocouple sensor measure the surface temperature of the cell, and we have the infrared thermal cameras. It's used to obtain the thermal image that are processed by few smart view infrared imaging analysis and reporting software. So the experimental results and validations for the battery cell and the step models, you can see that the mean values of R0 are estimated at each SOC values. So the R0 versus SOC at different temperatures. This temperature, take note, is the ambient temperatures. Observed in the R0 versus SOC, R0 remain quite independent at different SOC. So it's quite independent. Alright, so these are the fitting of points that we have obtained, okay, for different temperatures for R0. So as temperature increases, the value of R0 decreases. So this is the relationship we obtain, and this phenomenon is due to the high active reactions kinetics at higher temperatures. So this is how we try to fit the points, okay, by these equations. So the experiment results continues. So R0 at different ambient temperature across 12 cells. So we don't just look at only one cell, we look at 12 cells, and these are the 12 curves that you see. Alright, so we follow the similar trend, alright, of this exponential decrease, okay, for different cells. Alright, so this is only 12 cells. So if you try to work on more cells, you can find that there will be some deviations. So the experimental result has continued the mean value of R0 at different ambient temperatures as compared to its equivalent found in the literature. So R0 on the top is something that we have determined at different temperatures. So as compared in the literatures, okay, which I'll show you the reference later on, you will find that they are actually having a different value at different temperatures. Okay, and the absolute errors that you can see from each of these temperatures is around 0.07, 0.06. This is what we try to compare with the values that you find using the similar cell in the literatures. So the R1R C1 parameter is obtained, which is the next thing that we want to do, is by minimizing the voltage least square errors that we have mentioned. So R1 increased with higher temperatures. Okay, so this is something that we have determined from our experiments. Alright, and then the C1 will exhibit a fluctuation behavior with a few maximum and minimum points. So the relationship between SOC and C1 are quite compressed as compared to R1. Alright, so you can see that the relationship is quite complicated. Okay, there's sign functions. And the mean value of RCs and the mean square error of the terminal voltage at different ambient temperature, you can see that R1, C1 as such, and the terminal voltage and the errors, you can see that is quite reasonably small. And this graph that I tried to show to relate the past few slides that I should show, okay, on the R1 is the equations, okay, at different temperatures, and these are the C1. Alright. The next thing is that the terminal voltage increases at higher ambient temperatures and decreases at lower ambient temperatures. Alright, so you can see that for terminal voltage, we try to also measure at different ambient temperatures. You will find that increases at higher ambient temperatures and decreases at lower ambient temperatures. So although the terminal voltage is determined using the pulse current rate of 2 amps, the similar behavior can be obtained at a different load current as well. So 2 amps is considered quite a low current. So we compare the terminal voltage, the root mean square error at different ambient temperatures to the experiments. You can find that this is root mean square error in volts is around 0.1764 and 0.41. Alright, so in general, the terminal voltage is lower than 0.2 volts, and the RMSE is greater at higher and lower temperatures. And this is the observation that we make. So this is the graph that I want to show you. At 5 degrees Celsius, what is the terminal voltage? At 45 degrees Celsius, what is the terminal voltage? So the relationship between the OCV and SOC can be seen here. This is something that we have shown in a very early slide. Okay, so this is the relationship we try to establish, and you can see that the UOC depends on ambient temperatures. However, the UOC, which is the open circuit voltage, remain independent with ambient temperatures at SOC between 0.9 and approximately around 0.95. And a slightly high variation can occur at lower temperature of 5 degrees and 15 degrees Celsius, as we can observe from this graph. So we also need to estimate the nonlinear function, which is the F terms, okay, in this equation, if you can remember that. So we try to estimate it based on the input pulse current experiment data of SOC and OCV SOC relationship. So in general, the nonlinear terms reduces the rate of change in the terminal voltage by around minus 0.8 volts. And you can make some of this observation from here. So the result of the thermal model's parameters, alright, so the heat capacity and the resistance of the thermal model, namely the CC, CS, RC and RS, are used to investigate the sensitivity of the parameters. Okay, how sensitive is the parameters to the changes in surface and the core temperature of the cell. So as seen in the tables, you can find that the thermal parameters can vary at different temperature and even in different literatures, and also a type of cell. So in this simulation, the low color of 10 amps is used. So in simulation, we can use as high as we can. So we use 10 amps. So you can find that the resistance of the conductions RC has more impact on the core temperatures than the surface. So it implies that heat transfer is indeed at conduction mode. Okay, through metals, through any this material wise is conductions. So the resistance of convection means through the air. Alright, RS affect the surface temperature more than the core temperature, as it can be quite sensitive to changes in the resistance of convections due to the convective heat transfer. So the value of the thermal parameters as compared to the equivalent found in the literatures, okay, these are the parameters you try to look at, and this is what we have tried to estimate from our simulations. And you can see that from each of these references, you will find that they give different values. Some can be very high as compared to 3 or 4 Kelvin per watts, and some is quite close to one another. So you can see that the variation you can see is the highest variation I could see is the RS and followed by the CC. If you compare the estimated value as compared to the literatures. So the result of the sensitivity test on thermal model, so you will find that the heat capacity and the resistance of convections have more influence on the estimation of surface and the core temperatures. And you will find that it exhibits less dependence on core and surface temperatures. So the core temperature is higher than the surface temperature as heat dissipated from its core to the surface. So you can see that in the very early diagram, you will find that the heat actually dissipates from the core to the surface of the cell. So the difference between the surface and the core temperature based on nominal is around 2 kelvins. Okay, the result also indicate that the heat capacity CC and CS parameter can assume constant. So the variation of CS, which is on the left, and CC on the center, and RS on the right, on core and surface. So first plot is a surface followed by core, surface, core, surface, core. Alright, it's under the minus 30 to plus 30% uncertainty. So we try to vary at different temperatures. So what will be the effect of the CS, CC and RS? So you can see that CS rather constant at different temperatures, but not for CC and definitely not for RS. Okay, you can see there's some variation at different temperatures. So CC is at transient stage. So the RMSE, the root mean square error of the core and the surface temperature under these variations. So you can see that different core temperature RC, RS, CC, and C, as you can see from here. And similarly for the core and surface temperature under the 10% plus 30%. So these are the thermal parameters. So the RC, RS, CC, and CS, as you can see, 10%, 20%, 30% is highlighted at different colors. And the result of the electro-thermal battery step model, a total of 12 cells are connected in series, where the positive side of the cell is connected to the negative end of the next cell. So the cells are placed on this feature as mentioned before, and the thermocouple are used to measure the surface temperature of each cell, and they are placed underneath the cell, which is you do not see them in these pictures. And the core temperature is not measured, as we can mention to you, that is estimated through the least square approach. So the result of the electro-thermal battery step model, you can see that the surface temperature of each cell can be estimated. For each cell, let's say for cell 1, 2, 3, 4 to 12, you can try to estimate what is the surface temperatures. So the surface temperature increases linearly from cell 1 to 12 under the constant heat generation of each cell, and we assume that this surrounding ambient temperature is the same. And the thermal model show a good match with the surface temperature measurement of the K-type thermocouples. Just take note that the surface temperature is a temperature that is just above the surface of the cell. Okay, when we talk about the ambient temperature, is quite far away from the surface. Right, so you need to differentiate that. So the RMS between the surface measurement and the model of the battery stack is around 3 degrees Celsius. So the result of the electro-thermal battery stack model, the core temperature are slightly lower than the surface temperature when the cells are placed in the stack. So it can be contributed by the synergy energy of higher local temperatures and a lower current when placed near to one another. So it will cause a higher conductive heat transfer when the cells are connected in series. Because there's more metal part that's connected one another, so you can find that the conductive heat transfer actually will be higher. Okay, but the core temperature will be lower because it's being conducted faster away. So in addition, the smaller cells such as lithium-ion phosphate, ANR 26650M1B, has a better temperature distributions. So the result of the electro-thermal battery cell model, you can see that each cell can be estimated, the surface temperature increase. Thermal models show a good match with the surface temperature measurement as I mentioned before. This is something that I mentioned. So the RMSE of the surface temperature as compared to the nominal value is higher at minus 30 degrees than 30%. Okay, at lower uncertainty such as plus 10% and plus 20%, the RMS is lower, okay, than the thermal model uncertainty at minus 30% and minus 20%. So you can see that you can observe in the core temperature when the thermal parameters are perturbed by plus minus 30%. What it's trying to say here is that at lower uncertainty, the RMS error is lower, okay, as compared to higher uncertainty, which is a very logical way, because you have higher uncertainty, your this error will be higher. So you can see that you have a minus portions or minus 30%, which means the temperature actually go even lower. You find that this error is even higher. So it means that cell at lower temperature will face more uncertainty as compared to cell at higher temperatures. So in summary, the accurate modeling of the cell temperature is important. Okay, in the battery health monitorings, it's known that the internal resistance will increases, the temperature can increase due to higher heat generators. So despite the core and the surface temperature are identified, the electro-thermal cell model can become less accurate due to cell aging. Okay, this is something that we never touched on, but you know that if the cells age after many cycles of charge and discharge, you will find that the parameters will be a bit different. So by looking at the uncertainty, right, is very important. So by updating the parameter of R0 and RC pairs, which means R1, C1 for this case, it can improve the voltage estimation accuracies. But although we update the parameter can produce a better result, it can be quite challenging for actual implementations as the BMS consume higher computation resources, not forgetting that some they use AI and machine learning. Okay, that will even be more resource intensive, okay, in terms of hardware and the software. So the cost over the lifetime of battery application will be quite challenging. So in conclusion, the coupled electro-thermal state model is predicted both surface and core temperature of the cell and the battery stack was presented in these presentations. So we can see that the coupling between the electrical and thermal model enable the estimations of the voltage and the temperature under uncertainty. So uncertainty meaning that we have plus minus more than 30%. So we try to investigate on the parameter changes due to this uncertainty, and also due to the parameter change using the measurable inputs such as voltage, current, and ambient temperatures. So the main result of the battery cell can be summarized as shown. You can see that the open circuit voltage UOC remain quite independent with ambient temperature at SOC between 0.3 to 0.95 at 5 degrees and 15 degrees. And the thermal parameters such as RC, CC, and RS were identified as such. You will find that the variation of core and surface temperature of cell was quite high for RS and also CC. The value of RS depends on surrounding temperatures, will affect the accuracy of the core and surface temperature more than other parameters. The difference between the surface and ambient temperature was found to be around 3.6 K as compared to temperature between the core and surface at about 2 K. So here we use kelvins. So for the battery stack, okay, just now we are talking about battery cell, one cell. So what about the stack? So the root mean square error of the surface temperature between the measurements and the simulation of the battery cell was around 3 degrees Celsius. So the core temperatures will exhibit slightly lower surface temperature as all cells are placed in a stack, causing higher conductive heat transfer among the cell, resulting in lower core temperature, which is something that's quite good, that we can do some stacking of the cell so that you can help to increase the conductive heat transfers. But the future work, as mentioned, that this aging of cell is not being discussed, and we can also look into the wider this operating temperature in multiple electric vehicles in the real life applications, and the experimental uncertainty analysis and the hybrid pulse power characterization HPPC test will be performed to improve the accuracy of the model. So with that, I have to refer you to the publications that we published last year in the Journal of Energy Storage, which basically consists of the details and all the references that I mentioned in these presentations. So with that, thank you very much for your attention.